and this talk is about distributed storage, or in modern funding parlance, cloud storage. So the question that we're asking is, how do we make cloud storage more efficient? And we're concerned about both the space we're trying to save and also access times and so on. And the key intuition is, let's exploit the similarity between files to make this work. So first of all, why does distributed data storage even matter? The simple answer to that is, the big three think it matters, so it matters. But on a more serious note, there is just too much of data right now. We are concerned about faults, so we cannot have a centralized system. It won't scale. We'll have single points of failure. So the only way to go is distributed. You store this data across a lot of servers. And that's what the world is doing today through Amazon's Dynamo, which forms the backbone of its services, or Facebook's Cassandra, or again Google's Bigtable. All these three are very nice distributed storage systems. And these systems are concerned about many factors. We are focusing on two in this particular talk. The first is space efficiency. Minimize the space needed to store data. There are a million quotes out there. I just picked the first one that I could get. Data is increasing at a very high volume, so we need to somehow try to optimize over the amount we need to save. The second thing is access efficiency. And by access efficiency, what I mean is, we want to minimize the network access times taken to read and write the data. Again, this is an important parameter because this affects the end user directly. Like Amazon has to make such a guarantee for its services right now that 99 percentile of all customer requests will be satisfied within 400 milliseconds. So as far as space efficiency is concerned, one of the most prevalent techniques used in the real world today is deduplication. So deduplication is conceptually a pretty simple concept. All it says is that you have your files in the system, you break each file into fixed size chunks and eliminate the redundant chunks across the files. In doing that, you can make sure that you're at least representing the files in a very compact form. And it has been shown by a lot of results that compression rates in the range of 30 to 50% or even more actually can be obtained on places where you don't expect that much reduction, like web pages taken randomly from yahoo.com or CNN, file systems of a user. I mean, if the files are just versions of each other and you're told that they're very similar to each other, then you expect this kind of compression. But the beauty behind deduplication is it shows that even when there is no such expectation, you get a lot of compression. So let me just go through a very simple example. So here you have a set of files A1 to A5, and I have marked the colors wherever the bits are identical, and let's say we consider chopping them into 3-bit chunks. Now as you can see in this, for example, A1 and A3 has quite a bit of similarity, right? There are 000 shared and 110 shared. This is our general notion of similarity, that chunks are similar across the files. And how does deduplication work for these set of files? So what it will say is, rather than maintain all the blocks in these files, just maintain these 6 unique blocks, because these are the only unique 3-bit blocks appearing across all the files. The 3-bit is just a parameter. You could choose it to be anything, and there is a whole world out there which studies what is the best way to choose these things. So the next question is, currently the way deduplication is implemented is mostly in a centralized manner. You have files in a certain server. They try to maintain them as efficiently as possible. And for some reason, they haven't considered how we can do this in a distributed manner. I mean, there are cynical times when I think that industry just leaves these nice problems for us so that we can feel relevant once in a while as researchers and bridge the theory practice gap. But I think that their other concern is that whenever you take a centralized system and make it distributed, you start suffering because of network access times and consistency costs and so on. So what we are asking is, if you want to deduplicate files across a set of distributed servers, or rather to put it in a more abstract fashion, you want to exploit the similarity across the files in a distributed manner, how would you do it? So let's consider 3 approaches to this problem, which will kind of illustrate the motivation behind this work. You have those 5 files which I showed in the previous example, and let's say you're being told that you have servers which can at most hold 9 bits. And based on that, you want to store these files across these servers in a way that minimizes the number of servers used. Here is one solution. You know that there are only 6 unique blocks across these files. Take these blocks, pack them into the servers as tightly as possible, and since each block is at most 3 bits, you know that you'll require only 2 servers, because each server can hold 9 bits. Now this is, for this particular deduplication technique, this is clearly a space optimal solution. You can't do better than this. But this suffers from a problem, right? If I want to read or write to file A3, for example, I need to collect data across both the servers. And in general, if there are many servers in the system, this is going to have a lot of network access times, network messages, and because the chunks are across servers, consistency management issues. In general, it's not very easy to do it. Another solution is, okay, since you don't want to spread the file blocks across servers, let's just arbitrarily partition the files into separate parts or blocks and place them on servers and then apply deduplication on them. The problem with that approach is that, let's say we do it and we just say, okay, let's start with A1, A2, dump them on a server, deduplicate them. Then you are forced to use one server for A3 because it needs that many blocks, and again one more server for A4, A5. So this is what we call access efficient, because in order to read or write to any file, you don't need to go across the servers here, right? All the blocks of a particular file are within a server. But as you can see, this is not as space efficient as this solution. It's requiring one entire additional server. So can we somehow get the best of both these worlds? So let's consider this solution, which we call similarity-aware-partitioning. That is a technique that is partitioning the files in such a way that it keeps similar files together. So in this example, if you see, A1 and A3 have a lot of similar chunks. For example, given A3, you don't need any information from A1. So it makes sense to keep A1 and A3 together and A2, A4, A5 together. And by doing that, you get a solution that is again access efficient because the chunks are on the same server. But at the same time, it's also as space efficient as the first space optimal solution. Now, two things. For this simple example, just by inspecting the files, we knew what to keep together and what not to keep together. In general, this is not going to be easy. The main goal of this paper is, how do you come up with a general method for an arbitrary set of files that is efficient in both space and access times? Just stating what I said right now. And to state it formally, what we're trying to do is, given a set of servers, given a set of N files and a set of servers with a size capacity associated with it, we want to come up with some distribution of the chunks among the files in such a way that, obviously the definition is that each element of that distribution should contain chunks belonging to the files in F. Access efficiency. The chunks of any file should be contained in exactly one of the elements. You can think of these elements as actually servers hosting the files. And of course, space efficiency. The space required to represent any of these elements should be less than or equal to the server capacity C. So you can think of it as, we have these files, we separate them into K chunks, and we keep these chunks on K different servers. So just to illustrate what a KC distribution means, I'm going back to our example. So if you see, the chunk distribution solution is not a KC distribution, because to read A3 you're having to go across servers. Whereas both the second and third solutions are valid KC distributions. In this case it's 3, 9, because there are 3 servers each of size 9, and whereas that requires 2 servers each of size 9. It just helps us talk about the problem more easily. So one of the first things that we had to show was, generating a space optimal KC distribution is an NP-hard problem. So in general, this is not an easy problem, because deduplication demands that we look at all the files together, try to find which are the common blocks, and then try to see which kind of partitioning will keep similar files together. And it's pretty straightforward to show that it's NP-hard. The main question is, can we design polynomial time and bounded heuristics for this problem? So the key intuition behind our approach is to just use delta encoding or file similarities. So if you take nothing away from this talk, if one thing I would like you to remember, it's this, that you don't need to look at all the files to achieve good compression. Even if you look at them at 2 pairs at a time, a pair at a time, you can achieve compression almost as good as the entire set together. Just to define delta encoding, it's a very well-known concept actually. You have Unix diff, you have VC diff, GDiff. It's a well-established tool in order to calculate the incremental differences among the files. So in our example, if A1 has blocks B1, B2 and A3 has blocks B2, B4, B1, the delta of A3 given A1 essentially tells me the minimum amount of information I need to represent A3 given A1. So now given A1, I have the blocks B1 and B2. So the only information I need to represent A3 is B4, right? Because now given A1 and B4, I can reconstruct A3 completely. I apologize for this graph. This is the best I could make. But what's going on here is that we take each file and we create this graph in which the edge of each, the weight of each edge in this graph is the size of the difference between the two files. So intuitively, this graph is trying to capture the pairwise differences between all the files in the system. So why do we need this graph? Now, this graph tells me what is the most compact way in which I can maintain the files. If I just give you the delta encoding function, it's quite straightforward to see that the minimum branching or the spanning tree of this graph gives me the most efficient representation of these files just using delta encoding. Right now, forget the distributed servers and so on. We are just talking about you have some files, you have been given a pairwise function. How can I store them efficiently? It can be shown that you can construct that graph in the spanning tree. And for our example, it can be shown that in order to maintain A1 to A5, all you need to do is maintain A5 and a chain of such deltas. Now, if I want to recover, say, A4 in this situation, it's pretty easy. I have A5. I'll first decode A2 given A5 and delta, and then I will recover A4 given A2 and the delta of A4, A2. So this is complete information necessary to represent A1 to A5. So this intuition is important because this graph tells me that if I keep these files in this particular order, that is A5 and A2 together, A2, A4 together, these are files which have good similarity. That is the intuition behind this graph. It tells me which are the files that are similar, which are the files that are not very similar. So intuitively, A1 and A5 are not very similar. And now we have a story for how we can start partitioning it, right? That was the original problem. We said we have some files, we don't know how to partition them. We want to partition them in such a way that similar files are placed together. Now, given this intuition, now the fog is slightly clearing away. And now we can come up with an algorithm for how to generate a space-efficient KC distribution. So, to just put it in English, given a set of files, you want to partition them and store them across the servers so as to minimize the total space occupied. I no longer need to bother about access efficiency because it's almost encoded in my definition of the KC distribution. I will not even allow a definition in which chunks are separated across the servers. Now, how do I do it? This is our algorithm. So the input is the given set of files. So the first step is you generate the graph corresponding to the differences between these files, and then you generate the minimum branching of it. Like I said before, the minimum branching of it tells me the most efficient way in which I can store them just using the delta encoding operator. And now, given the graph, to create k partitions out of them, I can just trivially remove k-1 edges to generate k subtrees and place them on the servers. I'll give an example to make this more clear. There are many more fancy things that we can do in terms of removing the edges. This is just a simple idea that I'm giving because A, it satisfies our bounds and B, it's very simple to explain. But a lot more fancy things can be done to get different properties. And once you have your trees, after the partitioning algorithm, you just place the separate k subtrees on each of the servers using the delta encoding that we have discussed before. So one important thing to understand is the partitioning algorithm tells me how the files should be partitioned. After that, when you want to place them on the server, you can use deduplication, you can use compression, you can use whatever tool you want. But we show that even by just using the delta encoding, you can achieve very good space efficiency. So I'll go again to the example. We already saw that this is the minimum branching associated with the graph of A1 to A5. And now let's pick these two edges arbitrarily to remove. The fact that those are the heaviest edges is just a coincidence. It could have been anything. And now I want to place them across three servers. Because k was equal to 3, I needed to remove two edges to create 3 subtrees. Now I'll just place them on the servers. On S1, I'll just place A5. 0 has no information. On S2, I will place A2 and the delta of A4 given A2. And on S3, I will place A3 and the delta of A1 given A3. So, as you can see, within each file, I have enough information to regenerate all the necessary information for the files. For example, on S2, I can regenerate A4 just by using A2 and the delta, and so on. And this is the algorithm that we have for generating a KC distribution for an arbitrary set of files. The algorithm is interesting only because of the guarantees that it can give, right? I am no longer trying to come up with the most optimal deduplication based solution where I'm looking at all partitions. I'm obviously going to lose some space efficiency because of that. But how bad is it going to be? That's what this theorem is trying to tell me. So it says that, let's say you use our algorithm and generate a solution which requires a certain amount of space. We call that SSAP, or S Similarity-Aware-Partitioning. And let's say the most optimal solution to this problem requires a space of SOPT. We can show that the amount of space we require is tightly bounded by this expression, n minus k plus 4 into SOPT plus k minus 1 into S. Now, the k minus 1 into S is just an additive overhead. It's not significantly going to impact the system much. The significant overhead is the n minus k that we incur on top of the optimal solution. So, in general, when if it's order n times more than the optimal solution, this is not great news, but there are two caveats. One, the experiments will show that we in fact incur almost very little overhead as compared to the optimal solution. That's the first caveat. The second caveat is that for us to actually be order n times worse than the optimal, you need many chunks appearing in a lot of files, which is not a practical situation. In future versions of this paper, we are going to try and make some assumptions on the file distribution to come up with even better bounds. But it's tight, so it's the best we can do. And the other important thing when you are confronted with an NP-hard problem is to come up with a polynomial time algorithm to solve the problem. We can show that our algorithm has polynomial time complexity. It's pretty easy to see. All we do is construct a graph. There are n nodes, order n square comes from there. And apart from that, taking out k edges is just linear time. So we have achieved the goal we set out with, right? So we have a bunch of files. Now we can partition them in polynomial time. And we can do so in a way in which the space is also bounded. And this is nearing the end. So we implemented these algorithms in Java and tested them out for files randomly taken from Dropbox and CNN. And here are the four things that we are comparing. The block distribution is that centralized solution which is access inefficient, where you just take the unique chunks and distribute them across the servers. The random partitioning method is the one where you blindly just partition the files and put them on servers. SAP dedupe and SAP delta are our own solutions. In SAP delta, we maintain the files in the delta encoding format, and in the SAP dedupe, we maintain them in the deduplicated format. That's the only difference between them. The results on average say this, that on average we achieve 25% compression over the uncompressed set of files, whereas the randomized method achieves only 14.5% compression. So we are much better than the randomized method. The most optimal single server solution for this is 30%. So we are not that bad off as compared to the centralized solution. This was surprising to us to know that we only incur this much of an overhead. The CNN results are even better. So I'll conclude this talk. We defined the novel problem of finding a space efficient and access efficient solution for the distributed storage problem where we exploit similarity. We showed that the optimal solution is NP-hard. And just by considering pairwise differences, we can do quite well, quite near the most efficient solution possible. And finally, we provide you experimental verification from Dropbox and CNN. That's it. Thanks. Yeah.
So, access efficiency-wise, in case that you have multiple servers inside of the same data center, that your purpose may be different. You actually want to distribute chunk to the different server evenly, because you may access multiple servers at the same time, so that you actually can get all the chunks and then you actually can build, right? So that you can save your access time.
But why will you save access time with your distribution? I'm telling you, you don't even need to do that much work, right? I'm saying we'll just keep it on a single server and still achieve enough space efficiency.
So what I'm saying is that if you have a multiple server in the cloud,
correct,
data center, that really makes sense. But
yes.
In case that you have the multiple server in the same data center.
Okay, let's say they are in this room. Let's say there are laptops sitting in this room. What I'm saying is, even if it is that, we are only incurring an overhead of like 4% in terms of space, whereas I'm telling you that you don't need to talk across the laptops. So, I understand what you're saying. You're saying when network access times don't matter in a situation where they're within a data center or where the fiber optics make the network so fast. Even in such a situation, why would you want to distribute it when you can keep them like this? That's the question.
Yeah, because many of the partition or data
Correct.
or key values.
Correct.
So what they want to penalize all key value storage on multiple servers, so that actually you can save the time, evenly, maybe things like that. So in that situation, that people may ask that.
Fair enough. Fair enough. I see what you're saying. I see that there could be other trade-offs involved. Maybe the honest answer is, if we haven't explored all the trade-offs completely, it could be possible that in a situation where the network access times don't matter at all, like the one you said, right, within a data center or something, it is possible that maybe we can at least relax or compromise that every chunk should be within a server. Maybe we can start parameterizing it and say, fair enough. It could be that there will be other trade-offs involved. Yeah.
What are the files that you have used for duplication? Are they like text file, video file, which type of file? Kind of what I'm looking at, that if we just look at this blocking on, let's say, a source file, right?
Correct.
You just write a line of source within your source file, and you just cut them. None of these are similar, because basically there is a shift, right?
Yes.
And you don't consider that shift.
Yes. So let me. One thing I should have mentioned, but I didn't mention, is the deduplication definition that I have presented is a pretty naive definition. I have just said that you split them up into equal size chunks, but in the real world, deduplication is far more sophisticated, right? For example, they use Rabin fingerprinting to address some of the issues that you had suggested. The fact that you just update one thing and everything shifts and things go haywire. And we can inherit those techniques ourselves also to make deduplication as efficient as possible. So there are techniques that even we will use to make our systems more efficient. So you are correct. But to answer your first point as to what files these were, the CNN files were just randomly downloaded HTML files, and there were no video files among them. Typically, deduplication does very badly with images and video. It's generally really lousy, and I don't want to pay such a hard penalty for honesty. So I just kept HTML files. And as far as the Dropbox files are concerned, they were mostly text files. By text, it's just text files, right? These are files belonging to me and my collaborator Tia and Lan. So we just pick those files randomly and try to see what you're doing. But yeah, deduplication is not as simplistic as I made it to be, and because of that, the results won't change. In the next version, we will implement it using real-world deduplication tools rather than out-of-the-box Java thing that I have done in this time. Yeah.
One more question.
You thought about what happened to this scheme with one or more of the server spam?
That's again future work to think about fault tolerance. I was very adamant not to do fault tolerance this time because my thesis was on that. I wanted a differentiating factor, but now is the time to go into absolutely very
Well, thank you, Bharath. In the interest of time, let's move on.